Hello, this is Mr. Sorrentino again, and this is another video for Math 31. We're now moving into Chapter 5, and this is the first section of Chapter 5, which deals with inverse functions. And the reason why we're going to focus some attention on inverse functions in 5.1 is because that the rest of this particular chapter focuses on the relationship between a set of inverse functions, one being an exponential function, the other one being a logarithmic function. And since they are inverses of each other, and some of the characteristics we're going to note are because they are inverses, it becomes a good thing to focus our attention on knowing what inverse functions are and how they relate to one another based on them being inverses of each other. So we start with talking about an inverse relation first. Now, when I mentioned something about an inverse relation, it holds true for an inverse function too. But the inverse of a relation occurs when the domain and range are switched. That's basically all it is. So if I'm given like ordered pairs or a table of values like in example 1, all I have to do is reverse the coordinates. If I'm given a formula, I interchange the variables in the two variable equation, and then I typically solve for the new y variable. So for instance, this relation here, now this is a function. You notice that all the x values are only mentioned once. So, I mean, every x is paired with exactly one y. But if I want to say what the inverse is, my x's and y's interchange. So the x coordinates would be the 7, the 6, the 5, the 6, the 7. And the y's would be the -4, -2, 0, 2, and 4. Now, as you can see here, the inverse is not a function here. Because if you look at like an instance of the 7s as well as the 6s for the x's, a 7 produces a -4 and also a 4. The input or x value is 6 produces a y value of -2 and 2. So for those reasons, this is not a function. And you can also see that graphically. I also provide this on your notes. You know, this is what the original one looked like. So the original one is a function, but the new one isn't, because in two places, namely here and here, it fails the vertical line test. So when you have ordered pairs in some way, either in table form or if they were listed as points, all you do is reverse the x's and y's and you would have the inverse of that. If you have an equation, so like in example 2, if I can get this to move, here we go. I want to find the inverse of the following functions. Now these are functions. This is a linear function. This is a quadratic function. They're functions. There's a note down here. Even if a relation is a function, its inverse is not necessarily going to be one. And we want to be able to keep that in mind, because we're going to look for ways of determining how do we know if it is or is not the case. Well, the first thing I do, if it's written in function format, I'm going to replace f of x with y. And now I'm going to do the inverse. I usually indicate that I've done an inverse by putting a little I there with a circle. I mean, this is just my notation for it, because the reason why I want to note that is because if I put x in the place of y and vice versa, I'm changing what the x and the y are standing for. See, in this instance here, y was a function of x. Once I do the inverse at this point, y is no longer the function of x. Y is going to be the inverse of f of x. Now we have a notation for that if it ends up being a function. I have to see though if it's going to be a function. And the way I need to do that now is at this point, I now need to solve for the new y. So I want to get this y now by itself. I'm going to add 5 to both sides. Now I'm going to divide both sides by 2. So here y is going to equal, I could keep it as x plus 5 over 2 if I wanted to. I could also just distribute that and say that's 1/2 x plus 5/2. I could also write the 5/2 as 2.5. It doesn't matter. Well, this is in slope-intercept form. It's a line, and unless it's a vertical line, which this isn't, this is obviously slanted. It's going to be a function. So I can now stay at this point that, replace the y. I could say that the inverse of x, the inverse of f of x is 1/2 x plus 5/2. This is a function notation, okay? Which indicates that, that the inverse of this function is also a function. When I look at b, on the other hand, again, I'm going to let y equal f of x at first, and then I'm going to apply an inverse. So now I'm going to have x where y was and y where x was. Again, so a couple of notes. I'm not going to keep making these notes all the time. Here, y was equal to f of x. That was the assumption. That's why I was replaced one with the other. Here, however, y again is the inverse of f of x. Now, I don't know yet if it's a function or not, so I'm not going to start saying that y equals f negative 1 of x. If I could show that it's a function, okay, I'm done. I could then use the function notation. So I'm going to start solving this new equation for y. So I'm going to add 16 to both sides. And then I would need to square root both sides, but as usual, when I put a square root into a problem where it previously did not exist, that plus or minus symbol has to come with it. So I would end up with y equals plus or minus the square root of x plus 16. This is not a function. And therefore, I would not be able to write it in a notation like I had down here. This is not a function. The only way I'd be able to write this as a function, and I'll talk very, very briefly about this towards the end of this lesson, is if I restrict the range of this inverse, which means I should also restrict the domain of the original. And we'll get more into how those two things relate to each other. So, this is the best I could do for stating what the inverse would be. However, that's not a function, and that's not a function because we talked about it before, because this thing shows up. That gives me several instances. Like, for instance, if x were to equal 0, that would produce a y value of 4 as well as a y value of negative 4. Producing two y values from a single x value is a sign that you do not have a function. So, and again, you're showing some graphs of the situations to verify this. So in A, here's the original function, here's the inverse. Well, they're both lines. They both pass a vertical line test. They're both functions. Whereas here, if I have this parabola and I plotted these various points, these would be points on the parabola. If I would reverse, their coordinates and rewrite them this way, obviously this fails the vertical line test, horribly. So, there's not any x value except for negative 16 that only produces one y value. So it's not a function. So now let's talk about a few things that helps us figure out if a function would be an inverse function or not. A horizontal line test. It's very similar to the vertical line test. A vertical line test will help us determine if what we're looking at, a function, or if a relation's a function. The horizontal line test will allow us to determine whether or not the inverse of a relation is a function. So if I have a situation where I pass a horizontal line through the graph of a relation and that horizontal line passes through more than once, then I know for sure the inverse will not be a function. Now that could be instances where the original relation is not a function either, or it could be an instance where the original relation is a function, but the inverse is not going to be. Another term you're going to start seeing is is the term of being one-to-one functions. A function is one-to-one if and only if its inverse is also a function. That means that if you have a relation, it has to first be a function. So it has to be a one-to-one, let me emphasize it, a one-to-one function. You cannot have a one-to-one function if it's not first a function. So I've had students tell me that something was a one-to-one function, and if I said something along the lines of this, is this a one-to-one function? Well, they would do the horizontal line test. They say, well, horizontal line test, it passes the horizontal line test, it's a one-to-one function. Well, no, its inverse is a function, but the original relation is not a function. Therefore, it cannot be a one-to-one function. So you keep that in mind. It has to be a function first before it's a one-to-one function. Another term that you're going to see, let me scooch this down a little bit, some properties of these one-to-one functions. And we're going to show how to use these various things. So and we showed some of these already. If A doesn't equal B, then f of A doesn't equal f of B. So, if I have two x values, then, if they're not equal to each other, then the function values shouldn't equal each other. So that basically means, like, in instances where, like when I had like 7 produce 4 and -7 produce 4. Well, -7 and 7 are not the same. Therefore, for it to be a one-to-one function, the fact that I have f of 7 and f of -7 being the same, that's not a one-to-one function. So basically, different x values should always produce different y values. So I shouldn't see any repeating y values either. Terminology, as I've shown before, f of -1 of x is how we would indicate it's the inverse of f of x. So same thing, if I had the inverse of g of x, I'd say g -1 of x. I'm not raising this to the -1 power. Don't think of, we use this term for like inverse. Like it's like if I said 2 to the -1, that's 1/2. That's because 1/2 is a multiplicative inverse of 2. This -1 doesn't mean I'm taking the function and raising it to the -1 power, or I'm putting it in the denominator. So if I say, oh, here's f of x equaling x plus 2, f -1 of x is not me doing 1 over x plus 2. When I'm using it with function notation, this is not the case. This means that f -1 means inverse. It doesn't mean reciprocal. Okay, so keep that in mind. If it's a one-to-one function, the domain of f of x is the range of the inverse, and the range of f of x is the domain of the inverse. That's how we can sometimes more easily find domains and ranges when we have functions that are inverses, because at the point that I'm saying, well, I know what the domain is, I don't know what the range is. Well, if I find the inverse of that function and it still is a function, then I know that the domain of that new function will be the range of the previous of the one that I had done with the inverse of. And this is the last test we use for this. If I have two functions, and if I do a composition of those two functions in any order, and that comes out just to be x, then that shows me that those two are inverses of each other. So we're going to make use of these various properties to answer various questions for the remaining examples. So let's have a look at them. So for example 3, you're given some functions. You're given both the formula and you're given a graph, and you're asked to determine if the following functions are one-to-one. So these are all functions. You're going to notice with each one of these graphs, each one of these graphs do pass the vertical line test. We want to be able to show graphically and algebraically that they are also one-to-one. So basically what we have to do is find a way of determining if the inverse is also a function. So One way of doing that, if I have the graph, f of x equaling x squared minus 6x plus 8, it fails the horizontal line test. So I can say, from graphically, it's not one-to-one. As far as algebraically goes, I kind of outlined that before. How would I show algebraically that it's not one-to-one? Well, what I would do is rewrite it with y equals x squared minus 6x plus 8, and then I would find the inverse, which means the x and the y get changed around, so every x becomes a y, every y becomes an x. Now, here's the first instance. I'm trying to solve this for y. I want to get y equals something with an x in it. I mean, I would say f of x, but I don't know if it's a function yet. But I want to get y written as some expression of x. That means I don't want to have multiple y's in here. So I have to try to figure out ways of taking this equation here. Now, I don't have it set equal to 0. So I kind of lose my ability to use the quadratic formula. And I kind of lose my ability to use factoring because those only work when I have it set equal to 0. So for me to do this, the only way for me to possibly solve this and get y equals something in terms of x, I have to use completing the square. So what I'm going to do is I'm going to say, okay, I'm going to subtract the 8 from both sides. And I want to complete the square. And we've talked about this method before. I'm going to take half of this middle term. I'm going to square it, which makes the left-hand side a perfect square trinomial. I've added 9 to the left-hand side, though, which means I have to also add 9 to the right. I had to account for that. And so the y squared minus 6y plus 9 could be rewritten as y minus 3 squared is going to equal x plus 1. So now I only have one term that has a y in it. Everything else doesn't. I could use basic equation solving at this point to solve this. So scooching this down a little bit, I could square root both sides, and here's where I lose. Here's where it becomes evident that this is not going to be a function. When I take the square root of both sides, I'm treating y as the variable, so the non-variable side is the x plus 1. So when I square root that side, I have plus or minus the square root of x plus 1. And then when I add 3, I get y equals 3 plus or minus the square root of x plus 1. Because of that plus or minus symbol right here, there are values of x, say 0, where I could get more than one y value. Because if x is 0, y is going to be either equal to 3 plus the square root of 1, which would be 4, or y is going to equal 3 minus the square root of 1, which is 2. 0 as an x value producing two y values means that this inverse I came up with is not a function. So and that leads me to go back up to the same conclusion I made before. This is not one-to-one. So graphically, it's great if I had the graph in front of me. But graphing things could sometimes take a little bit of time, especially if you're not familiar with the function in front of you or you're out of practice with it. I mean, some of the graph transformation techniques we talked about in earlier chapters should be able to assist you now at this point with this. But in some of the quadratic features we talked about as well. But, algebraically, again, if I am finding the inverse and then trying to write it as a function, and the procedure and the process of doing that, as I solve for y, that plus or minus symbol comes up. As soon as that plus or minus symbol comes up, it's not a function. Getting to the next one, f of x equals the square root of x minus 1. As you can see, it's a function. It also passes the horizontal line test. No matter which horizontal line I draw through, it's only touching the graph once. So this passes the horizontal line test. And therefore I could say this is 1-to-1. How am I going to show this algebraically? Well, again, I'm going to replace f of x with y. Often with these functions, I should still be noting of the fact that, we don't have to get into this much detail with this. This is more so things you might have to do when you get to pre-calculus and such. Keep in mind that the domain has to be going from 1 to infinity, because if I have any value below 1, this won't exist. And we are talking about the positive square root. So my y value has to go from 0 to infinity. When I do the inverse of this, so applying the inverse, switch my y's with my x's, so this becomes an x, this becomes a y. I have my inverse. Now I want to solve for y, so I would square both sides. Squaring gets rid of square roots. And then I would add 1 to both sides. I'm just going to move the y to the other side, so I'm going to have y equals x squared plus 1. Nowhere in the process of doing this did I have to put a plus or minus symbol in. I got rid of a square root. I didn't bring one in. So, this is a function. Now, technically, from the other properties, this function would have to have a domain from 0 to infinity. Where you say, well, wait, it's a quadratic. It doesn't have it isn't going to have a domain restriction. Well, the other reason why this has a domain restriction technically is because the range of the original function was restricted, and the range of the original function is the domain of this one. And if I choose values of x that are 0 or more only, well, then my range would be values of 1 or more, which would be the original domain. So those get reversed as well. We don't usually get into this detail. This is kind of optional stuff for our purposes in this course. But I mean, we do know the domain from the graph we have in front of us, because of it being a radical function. But the domain of this function has become the range of the original one, and vice versa. So, that's what kind of makes this a function. Because if I just said, okay, if I had this being presented to me as the original function, this thing would not be 1-to-1, because x squared plus 1, y equals x squared plus 1 would produce another parabola like we had in A. Not the exact one we had in A, but very similar. And if that's what we have, parabolas are not going to be one-to-one functions. Therefore, for this inverse to be truly a function and go back for me to go to the original function still being a function, I have to have these restricted domains and ranges. Again, we're not going to get into that in that level of detail. Just this work over here is good enough, and for algebraically considering it, and that's simply just no plus or minus symbol had to come up out of this. For the next one, C, I'll use blue. I can see that no matter what horizontal line I put through this, it passes the horizontal line test. Gets a little bit iffy here because of the fact, but you have to remember, this is probably your horizontal asymptote. And as you can see, I know the horizontal asymptote for this based on what we've talked about before. Same degree on top and bottom, it's y equals 1. And this is happening when y equals 1, this line right here. So it's avoiding it like an asymptote, which means it's getting infinitely close, but the calculator's ability, it's going to probably just start putting a line at y equals 1 at that point because it's getting infinitely close, and I really can't demonstrate infinitely close by actually showing it's following that line at that point. So it is avoiding it. So, this does pass a horizontal line test. So graphically, it is one-to-one. It is a one-to-one function. And I could go through some things here. Again, I mean, as I do this, if I more at the level for, getting into pre-calculus and calculus, I had to look at this and say, okay, well, the domain is, everything but 3. And as we just discussed, the range, based on the graph I see, and me knowing about the horizontal asymptote, it's anything but 1. We're keeping this idea in the back of our mind. As I said, you don't necessarily have to do this. I'm doing this for the purpose of discussion when we get to example 5, and then we're going to kind of drop it. The algebra part is what you're responsible for. So if I wanted to find the inverse of this function algebraically and see if it was a function, I would set first y equals x minus 2 over x minus 3. I'm going to do my inverse, where I can now say that I have x equaling y minus 2 over y minus 3. Now again, my goal is to get y as some expression of x, which means I want y alone on one side, and on the other stuff I want to have x's, constants, and that's it. I don't want any y's on the right hand side. So I'm going to have to do some manipulation with this in order to get this solved for y and only y. Give myself some room here. Oh, and by the way, since this was a function over here, I just want to kind of get back to this before I can move on to this. This should now be written as f negative 1 of x equaling x squared plus 1. But technically, these things would have to be upheld. Is that we're not going to go that far with this, but since I've indicated that the inverse of the function was a function, that's what I would write for it. If I worked the other way around and had this as being the function, I would get that square root of x minus 1 being an inverse function, but I would have a plus or minus, and so I would say that the inverse is not a function. So unless I had some sort of domain and range, restrictions ahead of time. Get back over here. Okay. So what I'm going to do with this is I'm going to pretend as though that this is like x over 1, and I'm going to cross multiply. So I'm going to have x times y minus 3 equaling y minus 2, or make sure that's in parentheses. I want to get y alone on one side of this equation, but I had to make sure I got the one y out of the denominator. I'm going to distribute this x. Xy minus 3x equals y minus 2. In order for me to start working towards getting y alone, I'm going to get everything that has a y on one side of the equation and anything that doesn't have a y on the other. With that in mind, I'm going to subtract y from both sides, and I'm going to add 3x to both sides. So what happens here is, well, the y and minus y on this side cancel, the 3x and minus 3x on this side cancel. So I'm left on the left-hand side with x, y, minus y equals 3x minus 2. So all my y's are on one side of the equation. Now, if I didn't have multiple variables with this, if I just had this one variable and I had nothing but numbers, my terms on this left-hand side would probably be like terms that I can combine together. I can't combine these together because an xy term and a y term are not the same. I had to figure out a way, though, to get this down to having just a single y being mentioned. Well, both terms do have a y in it. This is like saying x times y, this first one. This one's like saying 1 times y. So I can look at this as being y times, factoring it out, x minus 1. And then when I divide both sides by x minus 1, that's the function I would get. It is a function because nowhere in the midst of me solving this did I have to use that plus or minus symbol. Every x value will produce exactly one y value. So I could then rewrite this now as an f negative 1 of x equaling 3x minus 2 over x minus 1. And if you would explore this further, you would be able to see that this one has a domain of everything but 1. Which you can see up here was the original range, or the original range. We brought that up. And therefore, and because of the test, we know it has a horizontal asymptote at y equals 3. And chances are this is a rather simplistic rational function. I would probably see the graph in its entirety avoid that y equals 3. I'd see that the range goes from negative infinity to 3, and then from 3 to infinity, so everything but 3 as well. Rational functions, tend to have a lot more cases where it's 1-to-1. Rational functions and linear functions, all linear functions are 1-to-1 except horizontal lines. All simple rational functions tend to be 1-to-1. You start getting ones with multiple vertical asymptotes and things like that, then it's a little sketchy. But generally, a lot of rational functions tend to be 1-to-1 as a result. Other functions, not so much. So let's look at the absolute value function. Well, graphically, it's a function we talked about before, and it does pass the vertical line test. It does not pass the horizontal line test. So I can say it's not 1-to-1. I don't know why I have a dash there. I shouldn't be there. It's not one-to-one. I can see that. It's failing the horizontal line test badly, which means if I do its inverse, it's going to tend to look more along the lines of this, and it's going to fail the vertical line test at that point. Um, how am I going to show this algebraically? Well, again, I'm going to let y equals the absolute value of x plus 5. That's rewritten instead of y. I'm putting y where f of x was, and I'm going to do the inverse again. So x is going to be the absolute value of y plus 5. I want to solve this for y. It's not very difficult to solve. I want to get that plus 5 away from the y, so a subtraction of 5 is going to happen sooner or later. But I can't move that 5 until the grouping symbol absolute values is gone. The only way to get rid of an absolute value is to, and now here's where we get into, possibly for extraneous solutions and things like that. We don't know what x is. X could be positive, x could be negative. We're going to assume it's positive. So we work under, anytime we work under an assumption, we get a possibility for extraneous solutions. I'm going to treat x as if it were positive, and I'm going to say, well, I know that y plus 5 then would equal either plus or minus x. I would usually say x or negative x, but same thing. This plus or minus right here automatically already tells me it's not going to be a function. So if I finish this off, I have that it's negative 5 plus or minus x. That is enough to indicate that it is not a function, because that plus or minus symbol means that values of x are going to produce more than one value of y. So I could say here, this is not a function. Which comes back up to here telling me it's not one-to-one, because I just did the inverse, and it's shown that the inverse is not a function. So that's generally how we go about doing it. Now for example 4, it's asking you to do a couple things. It's going to ask you to use the methodology that you're going to most often use to determine if two things are functions. But they also want to talk about the domain and range of the given function as well as the inverse. Now these are both rational functions, okay? I could talk about the domain and range first without actually going into the process of saying, are these in fact inverses? I want to verify that, but just to kind of move into the discussion we're going to have briefly in example 5, I'm going to look at domain and range of these two functions. Well, the domain for this one is pretty easy. It's all values of x except -1, because -1 would create a 0 in the denominator, and that means it won't exist at that point. I know this thing has a horizontal asymptote, at y equals 0, because I have degree 0 up here, degree 1 down here. And because of that, that means I have a situation where the highest power of the power of x on the highest power of x on top is smaller than the higher power of x on the bottom, which means we have a horizontal asymptote at y equals 0. Now, just because it has a horizontal asymptote there doesn't mean that the graph can't pass through it. If it passes through that asymptote, it's not a range restriction. But I have to say, okay, well, is it possible for 3 over x plus 1 to equal 0? I can do this, logically, which if you do it logically is fine. You just have to write out an explanation. Or I could do this algebraically. From a logic standpoint, if I take 3 and divide it by a number, I'm never going to get 0. I cannot divide a number by anything and end up with 0. It's impossible. I could get really close. I could get it to be really small, but it's not going to actually equal 0. I could also sit there and think of more of like cross multiplication. Well, if I assume this is allowed to happen, then if I cross multiply, I would be able to get 3 equals 0 times x plus 1, which means 3 would equal 0. Well, this is false. 3 does not equal 0. So to assume that y can equal 0 in this function it's not right. So now with this information all together, I could say that the range is anything but 0. So that works just fine. This other function, let's talk about the domain. Well, the only issue I'm going to have with the domain, for this one, is if x equals 0. So x should not be 0. Based on the same rules that we talked about, prior, this has a degree of 1, highest power of x. This has a degree of 1. Therefore, this should have a horizontal asymptote at y equals, it's a ratio of the leading coefficients. There's a -1 in front of that one, so it's -1 on top. There's a 1 in front of this one, 1 on the bottom. So -1 is a horizontal asymptote. Doesn't mean it's a domain restriction. So the thing I have to ask myself is, well, can 3 minus x over x equal -1? Well, let's find out. Assuming that it works, I cross multiply, I would get 3 minus x equaling -x. I would then add 0 to both. I would try to get x on one side by adding x to both sides, and that would give me that 3 equals 0 again. 3 equals 0, not 30. 30 equals, it's 3 equals 0. Which again is false. So I know that 3 minus x over x cannot equal that -1, which means that I can now state that the range for this is anything but -1. At least I've established so far that the domain of the domain of f of x is the range of f -1 of x, and that the range of f of x is the domain of f -1 of x. Having the domains and ranges like this does not make them inverses. That alone. I mean, so what I have to do is determine, do I in fact, if I go from, is f -1 of x, this is 3 minus x over x, in fact the inverse of 3 over x plus 1? That's what I had to determine. So one way that I've kind of already shown enough of, but I'm just going to mention it, is if I start with f of x and go through the process of letting f of x be y, do the inverse by switching x's and y's, and then solving, do I end up with this? If it happens, then that's a good enough way of showing it. The thing is, when you sometimes go that way, you have to make sure that it has the same format. And you have to kind of sometimes assume some things or realize that, okay, I can rewrite this as 3 over x minus 1, which is something we might get more often if we find the inverse of this using that procedure. That can sometimes throw students off because of the algebra involved. They might get an expression they think is not the inverse when in fact it is. So another method is to use that test that we talked about. And I'm going to rewrite it down here. to show f of x and f negative 1 of x for this particular instance are inverses, I'm going to show that f of f negative 1 of x equals x, and f negative 1 of f of x equals x. I'm going to run this test, and if this works, I have to show both of them. Now, if I do this and one of them doesn't come up to be x, then I know they're not inverses. So I can actually do this to show that things are not inverses as well. It's actually more streamlined, because as soon as I do the first one, if I do the composition and find out I don't get x as a result, then I know they're not inverses. I don't have to test the other way around. To show that they are inverses, though, I do have to show both of these. And that's because there are some functions, we're not going to study any of them in this course, but there are some functions that have, because remember, composition is not commutative. If I can compose them in one way and get x, but I can compose them in the other way and get something else. That would mean they're not inverses. So, going back to the two original functions, and to keep note of them, because I don't want to keep scrolling up and down. 3 over x plus 1, f negative 1 of x was indicated as being equal to 3 minus x over x. Let's see what happens when I do f negative 1 of x, which of course would be interpreted as this. Now, I have x in the parentheses, so I know I'm looking to get an expression. I'm not going to get just a number. I should get an expression, which x is an expression. So, which means the only thing I can really do, working my way from the innermost parentheses out, is I'm going to put the formula in here for f negative 1 of x. Which means I'm going to go to the function f of x and replace every x with a 3 minus x over x in its place. I have to simplify this. I mean, if for no other reason, that I don't really like having fractions with fractions in them. So if I can get rid of the fraction bar in the denominator, that would certainly be helpful. So I'm going to multiply the entire bottom by x, because that will get rid of the fraction in the denominator. But again, I can't do anything to the top on the bottom that I can't do on the top, because if I do that, I'm changing the value of it. So I'm going to multiply this by x over x, which means I'm multiplying this by 1. On top, I get 3x. On the bottom, I'm going to have to distribute that x. 3 minus x over x is just going to be 3 minus x. Positive 1 times x is going to be plus x. So I have 3 minus x plus x on the bottom. The minus x and plus x cancel. And that's simply over 3. I'm getting ahead of myself. I'm thinking of what I want, where it's going to happen. I'm putting that into place. I didn't want that either. There we go. Divided by 3, and that equals x. So far, I got that established. Now if I do f negative 1 of f of x, that's the same thing as f negative 1 of f of x. Working my way from the innermost parenthesis out, and again, recognize I'm going to get an expression. I'm going to replace what's inside here with 3 over x plus 1, because that's what f of x is. Which means I'm going to go to the function f negative 1 and replace every x with 3 over x plus 1. So I'm going to have 3 minus 3 over x plus 1 all over 3 over x plus 1. So now I have both the numerator and the denominator having fractions in them. However, if I multiply the top and bottom by x plus 1 over x plus 1 here, that's going to cause some cancellations to occur to allow me to simplify this. So I'm going to have 3 times the quantity x plus 1 minus 3 over 3, which gives me 3x plus 3 minus 3 over 3. These, of course, become nothing. I end up with 3x over 3, which is just equal to x. So I've proven that if I compose them in either direction, I get x, which allows me to conclude they are inverses. And so it stands to reason why we had some of the results we had above, where the domain of one was the range of the other and vice versa. So, remember that's having the domains and ranges behave that way does not make them inverses. It's a characteristic that inverses have, but it's a characteristic that doesn't make things inverses. This is a characteristic that makes things inverses. So if you're given two functions and said, are they inverses? Again, you could just take one of them, go through the process of finding its inverse, and see you end up with the same formula, being aware that it could have been simplified differently, so it might be harder to recognize, or you could use this test here, which means that the simplification doesn't matter as much as long as you know how to simplify to get to see like it can eventually become x or not, and then you're good. Now, as I said, example 5 it's listed as optional, and the reason why it's listed as optional in the previous versions of this course, if I started doing this flipped classroom model, I would usually only get into it if there was enough time in class. But I do want to talk about it only because of the fact that I think it makes some things about going into pre-calculus and calculus a little easier. And that's why I'm looking at these two domains from example 3. These were the ones that weren't one-to-one functions. And so when I look at these original functions and the original graphs, the original domain of this function was any real number, because I can put any real number into a quadratic function and get a number. The original range went from, well, this one had a vertex, and we can see where that vertex was on the graph. Looks like the vertex was at 3, -1. However, we could have also gone through the process of reproducing that, and showing that it's 3, -1 by saying, okay, well, x equals -b over 2a is where the x coordinate would be, because that'd be on the axis of symmetry. And if I do that, I have 6 over, or -6 over 2 times 1, which is the 3, and I plug 3 into this, I do get -1. And so we had that graph originally. There's a better picture of it, but I'm just going to kind of show it. Here's 3, -1, and the graph did something like this. But that was not a one-to-one function, because my range, well, that was the vertex. Sorry, take that back. The vertex was at 3, -1. The range was therefore -1 to infinity, because the lowest point was -1. And when we did the inverse of this, going back to the inverse, we came up with this. From our previous work, was y equals 3 plus or minus the square root of x minus 1. take that back, x plus 1. I wouldn't have an issue if the inverse was 3 plus the square root of x plus 1, or 3 minus the square root of x plus 1. If it was one of these but not one of these or the other but not both, it would be 1 to 1. So for me to restrict the domain of the original function f of x in order for me to make this 1 to 1, I don't want this to be negative infinity to infinity. I want this to produce only a specific range in the new function, which means that since I have two values for y here, my options are just to pick one. Now, I could pick either of them. I'm just going to pick this one. If I have y equaling 3 plus the square root of x plus 1, and I want to know stuff about this range, this goes back to some of our graph transformation things. We have a parent function of y equals the square root of x. This indicates, and y equals the square root of x, we know, starts at 0, 0. It's the lowest point. Then it has 1, 1, 2, 4, or 4, 2, 9, 3, so forth and so on. So we know that this has a range from 0 to infinity. But if I put the plus 1 inside the absolute value mark, it's going to cause me to shift left 1. That's not going to change my range. The 3 on the outside, though, is going to cause my range to go up by 3. So this, I expect to have a range going from 3 to infinity. In a very similar fashion, by the way, I would expect this one to have a range going from negative infinity up to as far as 3. Because the square root of something is always going to be 0 or more, then I would expect, if I add nothing or more, I'm going to get something that's 3 or more. If I have 3 and as I subtract nothing or more, I expect to get a value that's less than 3. Well, these would be one of your best options to restrict your domain. If I said here the range instead is now 3 to infinity, that means that I'm saying that only this part is what I'm considering part of the graph. The other part I'm more or less ignoring. And therefore it would be 1 to 1, because at that point, if I'm only looking at that half of the graph, it would pass the horizontal line test. So that's how you can determine a good way of restricting the domain. I could have also used this one and just dealt with the left side of the graph. So those are good ways of restricting the domain. Based on that, I want you to try the next one based on the absolute value and how it worked and what we've discussed about it before. So I want you to tell me, from the choices I'm going to give you, what would be a good restricted domain for this function to make it be 1 to 1. Well, getting to this one here, the original domain, well, I could put any number in to an absolute value function. Of course, the original range, since I'm taking the absolute value of something, I expect it to be 0 or more. And I can see this on the graph, going back to what we had for the graph, and I'm just making a quick sketch of this. Here's at negative 5. The graph did something along the lines of this. So it keeps going on. I mean, x values, it keeps assuming any x value. It just bottoms out at negative 5. And negative 5 is on the x-axis. It does not go below the x-axis, so I'm 0 or more. But this failed the vertical line test. So if I had the graph in front of me, I could actually take a shortcut about this, or I could look back at the fact that when I looked at my inverse, I either had y equals -5 plus x, or y equals -5 minus x. Those are what I resulted in. Um, these, if I find out like what these ranges would have, those would give me good ideas to restrict the domain of this function. Well, obviously, if I have y equals -5 plus x, that means I'm adding some number to -5. And remember, on the inverse, this x here is the range of the original function. So I know on the inverse, the domain are x values that are 0 or more. So if I'm adding a number that's 0 or more to -5, that means that -5 is going to be the smallest of those numbers. So the range is going to go from -5 and just keep getting bigger from there. If I have it the other way around, and I'm subtracting a number that's 0 or more, the -5 is going to be the biggest number I have. Just going to get smaller from there. One of these two would be the best way to restrict the domain. Again, I'm just going to choose this one here and say, okay, well, the restricted domain to make this 1-to-1 would be -5 to infinity. Because again, what I would be considering at that point is just this portion of the graph. The other portion I'd be ignoring, and if that's all the graph I'm considering, that is passing the horizontal line test. As I said, there are a couple of problems from the textbook that do walk through this and discuss this a little bit. You are not going to be held responsible for them, though, not necessarily. So make sure that you kind of know the idea behind it, especially if you want to get into pre-calculus and calculus, because they will be discussed there, and so hopefully it won't be too unfamiliar there. There are a couple of problems, I think, from the list that you have that actually ask about this, so you could actually work with that. However, this is something I'm not going to really quiz or test you on a whole lot. So, ultimately, what you're going to be asked to be able to do is to determine whether or not two functions are inverses, or if a function is 1-to-1 or not. That's it. I may throw a curveball and say, okay, if you have this function with this domain and range, is it 1-to-1? And that's something to consider. That kind of gets into this idea a little bit. So keep in mind that that might be on the way as well. But generally, you're mainly going to be responsible just for being able to find the inverse of a function, know what an inverse is, and determine whether or not two functions are inverses, often just by using that composition test. So, and that brings me to the end of what we needed to talk about in this lesson. So if you have any additional questions, please make sure to bring them up in class or come and see me during office hours. Until I see you in one of those situations, or until the next video, I bid you good day, and I'll see you around.